All right, AP Calculus. Here we are, Chapter 2. Get pumped, get psyched. Because now we're going to be going into the second part of our 3-part course. So we've now graduated from limits to derivatives. So we're going to talk about what the heck is a derivative, okay? And we're going to be on this idea of the derivative for quite a bit. So this is why we've now gone into this, what I would think of as a big chunk. And then the third big chunk is going to be integrals. But really derivatives is going to be where we're going to be at for quite a bit of time. So let's just get into it. What is a derivative? What does that measure? So one of the things that calculus tries to answer, one of the questions it tries to answer, is this question of how do I find the slope of a tangent line? Okay, so let's first think about, well, breaking that down a little bit. So we know that a tangent line is a line that touches a surface in exactly one location. So for the purposes of our kind of discussion here, I'm going to keep things fairly simple. So I'm going to pick a curved surface. So I'm going to say x squared. So you got like that. So there we go. So I'm going to write here f of x is x squared. So we got a curved surface here, and I'm going to draw a tangent line to that curved surface. So I'm going to do it here with this red line. Okay, so I know I'm doing this very poorly. Let me try doing this again, because I don't want it to look like this oddity here. So we know a tangent line touches the curve at a single point. Now, the other part is, okay, I got to find the slope of this tangent line. Okay, so that looks pretty good there. So I'm going to use that. Okay, there we go. Much better than doing it freehand. All right, so there we go. So there's my tangent line. Now, the other part of this is, okay, well, I got to find the slope of this line. Well, let's talk about slope. So, getting Sherman and setting our Wayback Machine to go back to when we took pre-algebra, algebra, geometry, and you had to find the slope of a line. Okay, so how do I do that? So I know that the slope of a line was y2 minus y1 over x2 minus x1. So I would have to have 2 points in order to find a slope. That's part of the formula. Now, for some of you science nerds or science buffs out there, you might also remember seeing it maybe like this, where the delta was the represented change. So the way we would read this was, oh, this is the change in y over the change in x. So really that's what slope was measuring, was a rate of change, how one thing was changing with respect to another thing changing. So this delta y, delta x. So slope was really measuring what we would say is an average rate of change. Now, why do I say the term average? Well, because what we're doing is we're starting somewhere, we're ending in another location, and then we're just kind of calculating a slope based on these kind of endpoints, these two locations. So the best way to kind of explain it would be to say, well, let's say, okay, from here to Tallahassee is like 500 miles. Okay, so from here to Tallahassee is 500 miles, so I get in my car, and it takes me 5 hours to get there. Well, okay, I traveled a total distance of 500 miles over 5 hours. So if I were to calculate that, I would say my rate was 100 miles per hour. That's an average. Because when I look at this number, I wouldn't say, well, you were constantly driving 100 miles per hour. There were probably some areas where you sped up. There were probably some areas where you were driving slow. There were probably some areas where you stopped. So it wasn't like it was a constant rate. This is why we would call this an average rate of change. Okay, so when we calculate slope, that's why we call this an average. Let me actually bring that back. We'll want to keep that. That's why we call it an average rate of change. Now, going back to our problem here that we have is, well, I want to calculate the slope of this red line. Oh, crap, there's a problem. I only have this singleton point. I can't calculate the slope of a line with just one point. So I'm going to give some definition here. I'm going to say this is 3, 9. So we're on that point on the graph. So I can't really find the slope. I just have 1 point. The formula needs 2 points. Well, what we can do is we could say, well, let's come up with a rough idea of what it is. Okay, so I need another point. So why don't I just pick another point on the graph? So I'm going to do this in green. So I'm going to pick this point over here in green that's on the graph, and I'm going to pick 2, 4. All right, so let's calculate the slope of that line. So I'm going to draw that line in here just to show. Okay, so a little bit. There we go. Oh, there we go. That's better. All right, so I'm going to connect those 2 lines. So now what I'm drawing here, remember, is a secant line. So secant lines go through more than 1 point. Okay, so this is not our tangent line. This is our secant line. So I'm going to put that in green. So secant. And the red is our goal. That's our tangent. All right, so let's calculate the slope of this secant line. So I'm going to call it m sub s, so slope of the secant. So we have y2 minus y1 over x2 minus x1. So this will be 5 over 1, so we get a slope of 5. Okay, so we got that. But remember, this is an approximation, so we could say, well, the slope of the tangent line's approximately 5. All right, well, what could I do to improve my tangent line? Well, or not my tangent line, but what could I do to improve my approximation? Well, if you get closer to the point of interest, I could get another line, which would probably, lean a little closer and match better this red line. So let's say I get a little bit closer and I go, okay, now I'm going to go and be at 2.5, and that's at 6.25. So I get even closer. So now what would be the slope of my secant line? Again, now would be 9 minus 6.25 over 3 minus 2.5. So when I do that, I now get an answer of 5.5. Okay, so you see my slope got a little bit more accurate. It's still an approximation, okay? However, we want to get even closer, all right? So, all right, let's get even closer. Let's say it's at, instead of there 2.5, let's get up to like 2.9. So now here's what I'm going to take out my calculator, because I'm going to get what 2.9 squared is. Contrary to popular belief, Mr. Surgery is not a calculator. I do not know this stuff off the top of my head. I know some stuff off the top of my head, but not squared numbers. All right, so 2.9 would be an 8.41. Okay, so now again, I'm going to calculate my secant slope. All right, so secant. So 9 minus 8.41 over 3 minus 2.9. All right, so go ahead and calculate that. So 0.1. So now we get a 5.9. So as I get closer, okay, my approximation's getting better. So I could keep doing this forever, right? I'm going to keep getting closer. Now, you might say, well, why don't we just get on top of the actual point? Like, why are we dancing around saying we're going to get closer and closer? Why don't we just get the same point? Because if we get exactly the same point, watch what happens. And some of you at home going, yeah, I know. But we want to illustrate that. If I get exactly on the same point, then I get indeterminate. So notice it's not that it's undefined. It's not that the slope is 0. It's that it's indeterminate. So remember that we just finished the chapter on limits saying, well, indeterminate means something. It's not that it's just 0 or a particular number. It could be any number. We don't know. So I already hinted at what essentially we're doing here. We are taking is a limit, because what are we doing? Oh, I'm approaching that blue point, but I don't want to be on the blue point, because if I'm on the blue point, boom, this thing falls apart. So what is it that I'm really doing here? Well, I'm approaching is 3. So I'm going to start writing out what have we been doing? Well, I've been calculating slope. So let's really now make that point abstract. So this green point is some arbitrary x value. And it's going to get closer. So the y value is x squared, because that's what the function is. So what am I doing? Oh, y2 minus y1 over x2 minus x1. And what I'm saying is, hey, let's approach 3, because that's what we're doing. We're taking our green point and getting closer and closer into 3. And that's what we're doing. So this that I wrote here is really my slope. And as we approach 3, then what we're saying is, as it gets closer and closer and closer, what is that slope of the tangent line going to be? So this now leans heavily on what we just finished doing in chapter 1. So let's finish this one off. So limit x approaches 3. So we can factor that top. That's going to be x minus 3, x plus 3, and then x minus 3. Those cancel. And now I have a continuous function, which is going to give me an answer of 6. And if you look at what we were doing here with our investigation, we were getting closer to that value. We saw, oh, we were approaching. So if we kept getting even closer and closer, I would say, oh yeah, I am approaching, and eventually going to hit that 6. So that's what the slope of the tangent line would be. So this is our first kind of dive into this concept of the derivative. And that's what a derivative is. The derivative is the calculus term for saying the slope of a tangent line. So we're going to be doing, I'm going to be doing a couple more videos, kind of doing some more examples of finding the slope of the tangent line and how we use this, and getting into like the mechanics behind it all throughout the course. So in the next couple of videos, what I'm going to do is just dive into a couple more examples, actually look at the definition that is in our book. Now, there's a couple of different definitions for the derivative. We're going to kind of break those down and understand what they mean, and then actually see how we apply them before we start getting into like the other stuff of how do we mechanically take derivatives. All right, so if you found this video to be useful, which I hope you did, hit a like on the bottom of the video, send me your comments and feedbacks, and I'll see you guys in the next video.